Hello again, everyone. Tonight I will finish this Tensor Flow implementation of the Mahalanobis distance. I sorted out what went wrong before. Well, it didn't go wrong. I just didn't get to it. You might recall I was working on this, and I'd gotten to the point where I had my two diff arrays, and I was trying so hard to think, how am I going to take all of my diffs in one column, one variable, against every other variable, and do this in an intelligent way. And so when I did it in Numpy, I of course did it with a for loop, which was maybe bad, but I did use the inner tools, not combinations, with replacement. So I avoided lots of trouble. I didn't do twice as much work as I needed to, because position ij in the matrix is the same as position ji. However, this is really just a premature optimization. If you imagine, what I really want to do here is I want to take every column of my matrix and dot it with every other column. With every, in fact, not every other, with every column, including itself. That is, I want to take the thing at position I, multiply by the thing at position ij, multiply by, say, the thing at position ij if I'm doing it against itself, and add that up for the entire column j. That's really what I want to do. And if I'd been thinking, I would have realized, oh right, idiot, that's called doing matrix multiplication. So that's what we're actually going to do. That does mean that nominally we're doing like twice as much work as we have to. But that's silly. Really, it's not going to affect us too bad. That's not something I would worry about until after writing your whole application and doing all this analysis, you realize, things aren't going as fast as I need them to go. Where's my bottleneck? And you realize the matrix multiplication is your bottleneck. So we're not going to need a for loop, in fact. We've got our diffs, right? Yes. It's going to be ridiculously simple. We're going to do tf.matrix multiplication. Now normally that takes a particular row gets dotted with a particular column, and that goes in a position. So we need to hit the diffs matrix, this one, with itself. And to make sure we do this properly, we're going to transpose diffs first. That just means we sort of swap what the rows and columns are. So this is a 2 by 100 matrix. Now it's going to be a 100 by 2 matrix. Boom. That's it. That replaces all this silliness. Let me put it in the proper covariance form here. Naturally, as always, things take 30 seconds to fix that I spent, 15 minutes racking my head on last time. Once I sat down and thought about it, clearly it was not that hard to do. And how did I actually solve it? I mean, I thought about it pretty hard, but this is the explanation that arrives after I've solved the problem. If we import numpy as np, we say numpy.covariance. Well, that's a function. What does it do? It computes the covariance. How does it actually compute the covariance? Use the double question mark. You can look at the source code for things that are actual Python functions. If it's a C function that's just exposed, you're not going to get a lot of information. Or if it's like, if the library underlying it uses swig. But in this case, you can get some useful information. Yeah, there's the help string, yada, yada, yada. Oh, I lied. It's not right there. Oh, it is. It is. There's a lot of stuff here. All I want to highlight is the last section. You're just doing a numpy dot dot, which in numpy dot is really the matrix multiplier. If you just take two matrices and use the asterisk to multiply them, that's an element-wise multiplication. So just things that are in matching positions get multiplied together. But the actual dot is a true matrix multiplication, like you learned in any linear algebra class or high school algebra. You know that they're taking x and x underscore t, which if you read through this, you find out is just x transpose. They're taking the conjugate, the complex conjugate, because if you're dealing with complex numbers, you don't just transpose, you invert the sign of all your complex numbers. I'm not going to worry about that right now, so that's okay. And they're doing x and then x transpose, whereas I do x transpose and then x, just because they're assuming that your matrix is, they sort of assume that you have the 2 by 100 matrix to start out with. You can fiddle with that in Numpy, of course. They're very good. But I'm assuming the opposite, and I'm not letting you fiddle with it. So that's really how I thought about. That's really how I found the answer, and then I went back and justified it to myself as, oh right, that's actually this. So, whatever helps you find that insight. That's the key. All right, so this is the covariance matrix. Boom, we got it. So that's how we create it. And then, now I remember how to use Tensor Flow, because you know it's been a week, haven't touched it. Here we go. We gotta have an answer, right? Yeah. Let's now run. I want as output my covariance matrix, and as input, alright, so we gotta put in some data. DD is gonna be data, of course. You note I've cheated a little bit because I've used this data.shape right here, but that's okay. And we are just gonna return answer. And hopefully that's quite all right. All right, let's rerun a lot of this stuff. Oh shoot. Well, that's fine. I sent that to the wrong pane. What? Breaking myself. There we go. Look at that. Much better. Beautiful, beautiful, beautiful. Let's turn off auto indentation like you do. Let's look at our various covariance constructions. We got numpy.covariance, which if I pass it, what is M? Estimate covariance given data and weights, right? You can actually do that up here. So this is sort of the baseline. That's our covariance. I believe that's about right. This is a quarter over here, a big number. Right. That's just a covariance matrix. Let's do it with our Numpy function that we wrote ourselves. I forgot to import iter tools. That was my fault. Did I? I really didn't. I only did it in IPython. I'm a terrible person. Like you do. Boom. Of course, now that means I should probably redefine this. There we go. Okay, do we get the same answer? Keep me honest. We do get the same answer. We get, in fact, we can even ask ourselves, are they really the same? Not exactly the same. I'm okay with that. They're close enough. And then the real question is our Tensor Flow version actually working? Let's find out. Boom, look at that. Here you notice I do get observably like different numerical answers, but things are essentially correct. I'm using 32-bit floats here. That could be part of the problem. If I use maybe 64-bit floats, maybe it'll be fine. Numpy in Python. Numpy, I would imagine, uses 64-bit floats. You know what? Let's find out. This is easy to change. Float 64 instead. Boom. Let's see if we get the same answer. Uh-huh. You might just look. Boom. Now they are numerically. Are they numerically exactly equivalent? They're like typeset different. This is in a list. This one. That's the big difference. A of 0. Yeah, A of 0 equals V. Look, some of them are even exactly the same. It's closer than the hand-rolled one. Funny how that works. Then again, I did implement it as logically the same. Okay. So that was all just to implement the covariance matrix. Because I wanted to be able to throw in my data and get the distance of every point from the mean, where distance is really the Mahalanobis distance. And I wanted to do this whole business in Tensor Flow, right? So let me grab my Tensor Flow function up here, and instead of taking in a couple of data points, I am going to take in a whole data set now, just like I do up here. I want to compute Mahalanobis distance of every point to the mean. That's what we want. Things that we need. We need these things. All right, so first we sort of need to compute this covariance matrix. So we do that. Excuse me. We don't have this XX and YY anymore. And what it's calling VV is really, for us, the covariance. So we just take matrix inverse of covariance. All right. Length of X is really the number of variables. Let's change that. Numvars. Okay. All right. Now here's what we got. We want to compute this distance. This whole little subroutine here. Here's the thing where TensorFlow is going to throw me off. I have a subroutine. I want to apply it to a bunch of things. I guess I can do this. Yeah, this is where I really want a tensor, because I really want that. Apply a bunch of matrix operations to some larger matrix, right? So diff. That's the difference between 2 points. But that's really already taken care of in diffs, which is the difference between all my points and the mean. Let's see. I want to see what happens if I say diffs of 0 in this place. So as though I'm just looking at the first point. Data, DD. There we go. All right, I just want to see what happens. I don't think, in the ideal world, this will return the distance, Mahalanobis distance, of the first data point to the mean. But let's see if it throws up in my face. It does. All right, that's fair. session equals tf.interactive session. And let me see what happens here. Let me just outline what all these things are. That that was not happy at all. There we go. Oh, nope, nope, still not happy. What went wrong here? Boop, boop, boop. So I was just trying to put it in my interactive session to get a better sense of what was going on. Yeah, diffs of 0 is probably not. Tensor shape dimension 100 must have rank 1. Okay, so I can't just pretend it's a vdict. So I'm going to try to compute diffs data, what the actual diffs are, and see what I can do with that. It should be dd is given by data. Might be part of my problem. Make sure I fix that right now. Data. Okay, much better. All right, so this is the actual diffs array, so that's a reasonable thing. Should have gotten more water. To soldier on. All right, we've got diffs. So many diffs, so many diffs. All right. And if I save that variable off, see here, it does let me just pull one off. But I suspect that's only because it's this eval thing. Yeah. All right, so that's not the right way to do that. All right, let's pause. What are we trying to do here? I need for every what am I doing to every one of my diffs? It all goes back to that Mahalanobis distance formula. Mahalanobis distance, thank you, excellent. Right, as always, we are trying to do this. The distance, element-wise, of every guy minus the mean. Ugh. Oh man, oh man, oh man. So I could keep this as some variable, compute all this, and then call my other function. I could have two separate sessions. One to compute the covariance matrix, and then another to loop through all of the variables. Oh, not all the variables. All the data points, excuse me. So it's the same problem I had last time. I just need to think of how do I structure this as a matrix solution. If I can get these dt and ds's, I need to do those for every single one of my guys. Maybe I can get away with this. Because after that, it's like an element-wise kind of thing. So if this is tf.diffs, instead of one numvars, it is numobs. Now it's numobs. So now this. All right, so now each. I gotta think about this real hard now. Jeez. Oh, I guess I don't even need to reshape it if I'm using everything. So that is superfluous. Right. When I transpose it, that's sort of built in what that is. DT stands for diffs transposed. DS stands for diffs the same or not transposed. Go figure. All right, now every column. Again, I have to pause, think about this real hard. Let's go back to this. So my matrix, my diffs, I already have what's on the inside. Yes, that I already have. So I need to multiply every one of these by the covariance matrix. All right? By the inverse covariance matrix, of course. So this is not going to work because I need like numobs copies of the covariance matrix, right? You like write this down on paper. That's the problem here. I'm so used to having paper to help me out, or like a whiteboard. That's not going to work too well for you guys though. So I will press on without that, attempting to do this. This may be another one of those videos where I bomb completely. Update the stream information. Excellent. Okay. Think about this some more. DT. I want one. Oh, brain, why don't you work? One row of DT to be matrix multiplied. You know what? I am going to. I do have a little miniature whiteboard. I just need to grab my eraser. I will be right back. 5 seconds, guaranteed. All right, I'm back. Erasing. Oh, jeez. Solving some linear programming problem on here. Erase all that. Oh man, this is the one that's cold. Hang on. Oh, much better, much better. Cold headphones in your ear, man. That's the worst. Yay. All right. So we've got DT right here. It was originally a 1 by v, sort of NV, num variables thing, times vi is a v by v thing. It's a number of variables by number of variables. So really, I've got, say, 0, 1, 2, oh no, 0 and 1, say. Cross. Let's go with 1, 2, 3, 4. Right, I've got this. Hopefully that's legible. And this is going to give me 1 by 2 by 2 by 2. Gives me another 1 by 2 guy. Let's call that AB. And that guy is, and the 1 by 2 guy gets multiplied by the 2 by 1 guy. Yes. That is correct. Right, so we're here. Watch me do basic linear algebra. Or watch me fail to do basic linear algebra. So if I've got a whole bunch of these things over on the left side here, let's say xi, yi, whatever, xi plus 1, yi plus 1, like so. When I do this multiplication, it's a row here times a column here. And that gives me this position. So if I just leave this matrix multiplication as is here, I should end up with a whole bunch of rows of the kind that I desire. Right? Yes, because every row is a different observation. I'm essentially hitting them all. Every row times every column, and that's going to give me a new row and column. Now when I right multiply, however, I gotta be careful. I'm gonna start now with, got some AB. I'm using terrible notation, xi, yi, whatever. I start with that after hitting it with the covariance matrix. And I am just hitting this I see. Yeah, here we go. 0, 1, WZ. My other, these are my observations in the other side. So that could be trouble. Oh, no, it's not. No, that's fine. Again, it's the power of matrix multiplication. Because this row is going to hit this column and give me a single number, which is exactly what I want. This is a whatever, n by 2, 100 by 2, and this is a 2 by 100. Oh, so I'm going to do some superfluous computations, right? Yeah, because I'm eventually going to take my second computation, my second like intermediate value here from the second observation. I'm going to hit that against the first column over here, which I don't actually need to do. There's just no reason to do that. So really, I'm going to do this computation, and I'm going to end up with a, in this case, 100 by 100 matrix. And I'm doing lots of extra work, and then I just pull off the diagonal of that, because that's every observation sort of hit with itself. And then I'll take the square root of every one of those numbers. So TF dot diag is the question. Surely there's a way to do this. Yes, if you're willing to if you're willing to do things more than once, matrix multiplication can do wonders for you. Diagonal. There we go. That decided to search Amazon. That's strange. Get the diagonal of matrix and Tensor Flow. Someone in Stack Overflow already knows. Don't double click for me, thanks. TFFX, someone's trying to make that too hard. Let me go to the API. TensorFlow.org, API, and we're looking at Python, which surprisingly has more, according to Google. Diag. Show me exactly what I want, come on. Returns a diagonal tensor with given diagonal values. That is not what I wanted. That creates a tensor from the diagonal. It will be possible, in the worst case, to strip off the diagonal with another multiplication, but I don't want to do that. All right, is there any other instances of diagonal? Same thing. Everything else padded with zeros. Hold down this for a little while just to make sure it cycles. Okay. Does not look like such an operation exists. Even if you extract it with matrix multiplication, it would not be efficient to get diagonal. Is order n. Extract. Oh, that's a terrible. You don't want to do that. tf.pack. What is that? Packs a list of rank R tensors into one rank R plus 1 tensor. So rank R Backs tensors and values into a tensor with rank 1 higher. Numpy.array xyz. Interesting. All right, so really, if I want to extract the identity, or not the identity, excuse me, I want to extract the diagonal. I've got a big square matrix here. And I've got a bunch of garbage, and I got some pristine values on the diagonal. If I want to get those, it's 100 by 100, say. I want to end up with 100 values, so I'm going to hit it with something that's 100 by 1. Naturally. What kind of matrix am I going to hit it with? It's every row times every row of this hits every column, hits the one column. So if I just have a column vector of all ones and I multiply it by that, I believe that will give me what I want. So let's do that. TF dot matrix multiply of M2, comma, TF, this is a constant now. Let's see if I remember how to use constant. TF dot constant, there we go, yeah. Really, I just need to remember, is it lowercase, yes or no? TF dot constant. Oh no, TF dot ones, even better. Should have guessed there was something like that. And TF dot ones, we just input a shape, which I want to be number. Oh, I need an actual shape. Is TF dot shape a thing? Is the question. TF dot shape. Can I use it to define a shape? I bet we can just do this. Numobs 1. Right, I just have a column. Each of these ones is essentially just saying, yes, pull out that row. Yes, pull out that row. Yes, pull out that row. Hang on, is this right? Every row is going to get hit with every... No, this isn't right. Oh my gosh. Because I've got garbage in these positions. And this is saying, keep those positions. That's terrible. That's not what I want. All right, well, that's good. I didn't finish that. All right, so we've got to think a little harder about this. Because I want... Right. Got this variable. I want the first one from the first guy and the second one from the second guy. If I hit it with the identity, but no, that doesn't get them. That doesn't end up putting them in the right positions. Let me go back to Stack Overflow. Tensor Flow extract. Let's see what happens if I say I want to extract the diagonal. We'll open that back up. Oh, TF where? How can I get the diagonal values on a matrix? Oh, that's, here we go. No, that's not it. Looking through the math operations, use tf.pack. Ugh, that doesn't seem like the right thing to do. XII. This doesn't seem like the right thing to do. Let's write up your own op in C++, rebuild TF and use it natively. I think it's really cute. This guy's name is Theon No, as though he really hates the other machine learning library, Theano. That's really funny. I just noticed that. I can't believe this question got -1. Jeez. It's a reasonable question to ask, right? What is batch matrix multiply? That's not what I want to do, but multiply slices of two tensors in batches. No, that's not what I want. Matrix inverse, batch matrix inverse, Cholesky. I forget what Cholesky is. No. Complex, imaginary, real. Reduce sum. Reduce prod, reduce min, reduce max, reduce yada yada yada. Not really reducing. I'm sort of reducing. What does segment stuff do? Beat sum along segments of a tensor. No, that's not what I want. Sparse segment, argmax, list-diff, where. Turns locations of true values in a Boolean tensor. Turns the coordinates of true elements in input. Coordinates returned in a 2D tensor. So maybe I can use this. If I just pass the identity matrix of the appropriate size into tf.where, I'll get trues along the diagonal. And then where input true has 5 true values. Oh, what is this? Input has rank 3, so its coordinates have 3 indices. Where does this 2 come from? Coordinates returned in a 2D tensor with the first dimension, rows, represents the number of true elements. The second dimension, columns, represents the coordinates of the true elements. Keep in mind, the shape of the output tensor can vary depending on how many true values there are in the input. Yeah. It'd be nice if they had a example with this. What's index? I thought there was a... Is there just a tf.index? IDX? That's... no, not bookmarked. Although, yes, maybe I should bookmark it. tf.idx? Is that a thing? tf.identity. Turn a tensor with the same shape and contents as the input tensor. That's not what I want. Let's do a general search. Just extract matrix diagonal. Because I don't want to have to use this pack thing. But I will if I have to. MathWorks. Okay, that's for MATLAB then? Yeah. Again, that's for creating. That's not... Create diagonal matrix or get diagonal elements of a matrix. Oh, they can do either. Well, aren't they special? Rand I, diag A. Extract diagonal of a matrix. That's doing it in R. Diag to vec, yada yada yada. You can do it with a sequence of matrix multiplies and adds. Oh, this isn't a bad idea here. If we use this matrix first, so instead of all ones, we have just a 1 at the top. We do that multiply. That gives us a 100 by 1 thing. All right, I know how to do this now. That's going to give us a 100 by 1 thing. And it's going to be 0 everywhere except in that first position. In that first position, it's going to have x0. So we add this whole result, this whole new 100 by 1 matrix to some 100 by 1 matrix of all zeros. Then we're going to multiply our matrix again. But this time, we're going to have the 1 in the second position. So we're going to get the second row. And again, and again, and again, and again, and again. And we can do this. God, this still seems like I'm going to need like a for loop at the end. Or like I just need a for loop to go through all these stupid things. It's like, I don't want every row with every column. I just want some rows with some columns. All right. Let's try another line of avenue of attack here. Let's consider, does Mahalanobis Distance... So I'm also killing myself because I'm doing this before implementing it in Numpy, where it might be a little easier to think about. Let's see if someone has implemented it in Numpy. Mahalanobis Distance. Mahalanobis Distance. Numpy mean. So compare every data point to the mean. That's... Oh, what does exist in SciPy? Seriously? Oh man, I feel like an idiot. Mahalanobis. Boom. C-dist. What is VI? VI is the inverse of the matrix. Between the points, Mahalanobis distance between 2 points, U and V is yada yada, this thing. If VI is not none, VI will be used as the inverse covariance matrix. I wonder how it computes it if it doesn't know it. I did not know there was this many distances you could compute. Wow. That's impressive. Computes distance between all pairs of efforts using supply two arity function F. Yeah. Alright, so what is this in? SciPy, that spatial, that distance, dot c-dis? Let's see if I can do that. I might not actually have SciPy installed on this Python too. Is c-dist. A module named c-dist. Okay. Distance? No. SciPy dot spatial. Dot distance. Dot c-dist. Oh, there. Oh, I see. It's built in. Mahalanobis. All right. So yes, this tells me exactly what I knew before. That's the Mahalanobis distance. And how do they do it? Yeah, they do it pretty much like I do. They make sure their vectors are good. They compute the inverse matrix of the covariance. They dot things just like I do. Take the diffs, dot it with VI, dot those with the other. Take the diffs, dot that on the right-hand side. Take the square root of the whole thing. So they're not doing anything fancy here. All right, let's see. Oh my gosh, is it seriously? I've been going for 40 minutes and I've been getting nowhere for 40 minutes. Jeez. Once again, I'm fooled. All right, let's look at the pack thing. We'll try that. Use tf.pack in the way Anurag suggested. What does he suggest? He's got a 3x3 matrix. He makes another thing that's just pack. He packs that matrix into it. Oh gosh. All right, we'll try it. And then it gets evaled. Okay. Tensor Flow. I just use TF. Right. Frying range num obs. And it's not X, we're going to be using M2, right? Yeah. M2 being the large array of lots of extra crap. It's good to know that like you can just do this, so if I need to extract certain things. Z is a fine name for that. I'm happy with that. Z. Hey, there we go. Okay. Let's Let me recreate some of these things. Diffs. Make it work a little better. Oh, dimensions are not compatible. Of course not. Of course not. What is DT? DT.shape. Tensor object is no attribute shape. Didn't think that was true. DT.getShape. Naturally. Get shape, like that. There we go. Okay, okay. I have 2 rows and 100 columns. And vi dot get shape, of course, if I can spell correctly, has 2 rows and 2 columns. I guess I didn't want to transpose this. What am I? Because normally this would be 2 rows and 1 column? Oh boy, let me tell you. Buddy. Let me grab these guys again. Just to see what I did here, if that was wrong. Ah, so over here I changed it to 1 row and 2 columns. Whereas it originally would have been 2 rows and 1 column. Interesting. That's interesting. So, what if I do this the other way? Oh, what did I do? Oh, Alright. Change this to S. Change this to T. Let's see what happens, shall we? So it's happy about the sizes of those things. It probably doesn't matter. Probably not. Really? I honestly expected it to yell at me about square root. But square root is probably smart and returns square root of x element wise. Huzzah! That's the whole thing then. Let's give it a shot. Let's just try it, shall we? TF Maha of data, let's blow up in my face. Kaboom. Numpy.shape of our answer, first thing. Like that. 100. That is the correct shape, at least. Alright, so in that case, let's compare that to the Mahalanobis distance between every... Do I have diffs? No. D's not defined. Okay. Data 0, data 1, those are a whole bunch of points. Right. If I take the numpy.mean of data, axis equals 1, I want 2 things, axis equals 0, there we go. So, if I say Maha of x, comma this, comma v, for x in data. So this is using Numpy essentially. This is what? All Maha, we'll call this. And of course, I haven't actually defined this function. This is just all I want to check what's going on. There's no attribute I. Right. Because I have to put in the matrix. VM is not defined. Now it is. Magic. And I get a whole bunch of miniature matrices back. that's all those. And if we go back to where we computed it with Tensor Flow, here we go. Okay. TF all Maha. Ding. Okay. And then let's just look at all those together. TF all Maha. I'd say T comma N for T comma N in TF all Maha. I mean zip. Simple Python eludes me sometimes, you know. And all Maha. N is not defined because I also can't spell. That didn't work. All Maha 0. No. Not all Maha 0. Opposite. There we go. There we go. And in fact, I know that this is going to be 0. I know it's going to be 0, comma 0. There we go. And now, instead of... Let's take the difference, see how different these numbers all are. As you can see, these are all pretty small, on the order of 10 to the negative 16. Yeah, sorry. Numpy.log of 1e negative 16, comma 2. Must be of array type. I didn't know I could do that. I can't say the base? Well, that's unfortunate. Divided by numpy.log. Do our change of base there. There we go. So using 64-bit floats, if our error is very, very small like this, I'm willing to accept that. You can see that we pretty much did. We have matched the actual implementation here of Mahalanobis Distance with Tensor Flow entirely, all of it in Tensor Flow. You just put in the data, and you say, give me back all the distances to the mean. And like magic, it happens. Except instead of magic, it was a lot of banging our head and maybe cheating with this tf.pack thing. Yeah, it would be nice if there was a way to just get the diagonal back super easy. This honestly isn't that bad. And you know what, as I think about it, like, okay, I'll probably end up using this again in the future. It's nice to know that I can just pass this thing into pack and it'll do the right thing. And so yes, I do have a small for loop inside my Tensor Flow. Maybe that makes me a terrible person. That's okay. I'm willing to live with it. So yeah, now we have a full implementation of Mahalanobis Distance. I think that's all that I want to cover tonight. I believe next week I will still be streaming. On what exactly, I'm not sure. I might just do kind of a wrap-up thing on TensorFlow. Like, these are the things I learned, or maybe I'll try to get some of these cool visualizations working. That looks cool. Would I be able to do that? Maybe not. Or maybe I'll do another tutorial, something like that. They've got some pretty interesting ones here with the recurrent networks. Maybe I'll do partial differential equations. PDEs. I at least have a little more experience with PDEs than with like neural networks. So maybe that would make more sense. Oh, hey, Pill. I've used that before. That would be more installing stuff, and you get to see me fool with that. Always a good time. Or maybe something else. I don't know. If you have something you want me to talk about, leave a comment, send me an email, write me a letter, whatever you want to do, and I'll see what I can do. And then week after next, I'll be off, and we'll start the new year, and we'll think of something else that I want to work on. I'm thinking about Theano, but might be something else. All right. Thanks, everybody, for watching. You have a good night.